Good day to Dr. Nas. I am Siti Mahira binti Muhammad Ibrahim, the group leader of Group 5. Today, we are going to present our finding of modeling and optimization of an industrial Rankine steam cycle using MS Excel, a case study for the Samajaya Free Industrial Zone. In response to rising energy demand and the urgent need for industrial energy efficiency, this project presents a comprehensive thermodynamic design and optimization of a steady-state Rankine steam cycle conducted by Yellow Hippo's company. The system is tailored to meet the utility requirements of a specific industrial client in the Samajaya Free Industrial Zone, Kuching, using a customized Microsoft Excel computational mode framework utilizing iterative convergence logic. A baseline of 15 MW net power system was modeled. Parametric analysis is revealed that while increasing turbine inlet pressure enhances thermal efficiency, it is ultimately constrained by the critical steam quality threshold of X more than equal 0.85, required to prevent lead erosion. To meet the secondary objective of scaling the plant of 35 MW, a modification strategy of aggressive parameter elevation was evaluated. Results indicate that the baseline 15 MW system operates at 39% thermal efficiency with a mass flow of 11.262 kilo over second, while the optimized 35 MW configuration achieved a peak efficiency at 50%. This study concludes that while parameter scaling is effective for capacity expansion, structural cycle adaptations such as reheating are necessary to ensure long-term mechanical reliability at high-pressure boundaries. Since global energy demand is increasing, leading to high carbon dioxide emissions and significant energy losses from industrial systems, around 50% of heat in power plants is wasted as low-grade thermal energy, highlighting the need for improved energy recovery methods. The Rankine cycle remains a key system for converting heat into electricity and is widely used due to its flexibility and efficiency. This project focused on designing and optimizing a steady-state Rankine cycle for an industrial client in Kuching, with the aim of improving performance and scaling power output from 12 MW to 35 MW using thermodynamic optimization technique and cycle modification. Now we are going into the methodology part. First is development of the baseline 15 MW Rankine cycle, a simple Rankine cycle consisting of a boiler, turbine, condenser, and pump was selected. System properties were obtained from steam table, and operating parameters were determined based on standard thermodynamic references. Second, Microsoft Excel programming simulation. The Rankine cycle was modeled using Microsoft Excel. Thermodynamic properties and energy equation were programmed into the spreadsheet. The model was adjusted until the net power output reached approximately 15 MW. Third is mass and energy balance analysis. Steady state operation was assumed. First law of thermodynamics was applied to each component. Turbine work, pump work, heat input, and heat rejection were calculated. Fourth one is determination of thermal efficiency. Thermal efficiency was calculated using NTH equal to W net over Q in multiplied with 100%. The efficiency was used to evaluate the cycle performance. The fifth is scaling and modification of 35 MW. Modification were introduced to increase output from 15 MW to 35 MW. Enhancement method included increasing turbine condition and applying reheating or regeneration. The modified cycle was compared with the baseline design. Last is engineering assumption, steady state, steady flow condition, negligible kinetic and potential energy changes, no heat loss to surrounding, water use as the working fluid, constant turbine and pump efficiency, constant condenser pressure, and lastly is steam properties obtained from standard steam table. For the result and discussion part, system modeled, steady-state industrial Rankine steam cycle, power plant via MS Excel, parametric analysis variables, turbine inlet pressure, superheat temperature, and condenser operating pressure. For the target is baseline 15 MW net power with turbine exhaust steam quality more than 88% to prevent blade erosion. Scale capacity to a height throughout 35 MW net configuration for Samajaya Free Industrial Zone. For Microsoft Excel simulation platform, Workbook architecture, a flexible, steady-state computational platform with interconnected sections for input, lookup table, state calculation, energy balances, and cycle analysis. User-defined variables. It allows direct modification of boiler, pressure temperature, condenser pressure, component efficiency, and target net power input. Users built in Excel functions to automatically retrieve enthalpy and entropy from embedded steam tables. It is to ensure computational consistency. Thermodynamic equation, standard equation for the pump, boiler, turbine, and condenser are implemented via linked cell formulas to rapidly calculate. This is for net-specific work output and required steam mass flow rate, boiler heat input, and condenser heat rejection. Lastly is overall cycle thermal efficiency.
Moving on to section 3.2, baseline sensitivity protocol, our primary analytical objective here is evaluating steady-state baseline performance to verify design feasibility for a 15 megawatt net power output. To isolate direct impacts on thermal efficiency and specific network, we utilize a one-factor at a time methodology, systematically varying a single operational boundary while holding all other variables constant. Mechanistically, shifting subcritical pressures and temperatures alters fluid enthalpy boundaries. This directly shifts both the boiler heat addition line and the turbine expansion trajectory. Ultimately, this protocol acts as a critical diagnostic and structural safety tool. It pinpoints the optimal thermodynamic balance to maximize power generation without accelerating mechanical or thermal degradation. For example, while high boiler pressures maximize Carnot efficiency, they simultaneously escalate piping wall stresses. Conversely, deep condenser vacuums expand network but introduce risk of ambient vacuum leaks and severe turbine blade moisture exposure. Moving into section 3.2.1, let's look at the characterization of our steady-state thermodynamics baseline states. To establish a comprehensive thermodynamic profile for our baseline 50 megawatt subcritical Rankine cycle, we extracted primary state points across 4 major operational boundaries directly from our simulation. As you can see in table 1, we have compiled the precise steady state values for pressure, temperature, specific enthalpy, specific entropy at each key stage. This tracking spans from state 1 to initial superheated turbine inlet operating at 5 megapascals and 600 degrees Celsius, all the way down to state 4 at the compressed liquid pump outlet. These values define the core physical properties that drive our baseline cycle's overall performance. To verify the physical and computational integrity of our simulated system, we perform a comprehensive energy balance based on the calculated steam flow rate, which was iterated via call seek to exactly 11.262 kilograms per second. Looking at table 2, we detail the specific thermodynamic formulas and steady-state values for our key performance metrics. Our turbine power output reaches just over 15,000 kilowatts, balanced against a pump power input of 56.84 kilowatts, with a boiler heat input of nearly 38,873 kilowatts and a condenser heat rejection of about 23,872 kilowatts. Our net power output lands precisely on our 15 megawatt industrial power target. This brings our baseline cycle thermal efficiency to a solid 39.0%. Next, in section 3.2.2, we evaluate the turbine expansion performance and its efficiency limits. The thermodynamic performance and thermal conversion capacity of a steam Rankine cycle are fundamentally governed by how the working fluid behaves as it expands across the turbine stage. To evaluate our operational limits, it is vital to analyze how shifting high pressure and high temperature boundaries alters the available enthalpy drop across the blades. In this section, we examine the dynamic responses of the steam expansion line when exposed to both low pressure limitations and elevated supercritical boundaries. Specifically, our analytical focus area center on 3 tactics: increasing boiler pressure to maximize specific work potential, elevating turbine inlet temperatures to safeguard lower pressure stage against premature condensation, and minimizing back pressure to maximize overall expansion length without violating vacuum safety or blade erosion thresholds. Let's zoom into section 3.2.2.1 to look at the dynamic response at a low operating pressure boundary. Operating the Rankine cycle at a low boiler pressure, for instance, dropping below our 5 megapascal baseline, inherently lowers the average temperature of heat addition. This temperature drop directly reduces the specific enthalpy drop available for conversion into mechanical work inside the turbine. Now, while lower pressures do offer a benefit by reducing mechanical stress on the boiler and piping systems, they create massive disadvantages in system size. To maintain the exact same power output at a lower pressure, a much higher steam mass flow rate is required. This drastically increases the necessary size of the pipes, turbines, and other plant components. This behavior closely mirrors low temperature waste heat recovery systems, where lower thermal energy always results in lower power output and demands much larger fluid flow rates to compensate. So now, let's look at the opposite end of the spectrum, the dynamic response at optimal and upper operating pressure boundaries. For this phase, simulation parameters were shifted to an aggressive upper boundary featuring a supercritical pressure of 40 megapascals and a superheated temperature of 900 degrees Celsius, aiming for a proposed 35 megawatt output. These higher pressures and temperatures massively improve cycle performance. At step 1, the inlet enthalpy increases to 4,253 kilojoules per kilogram while entropy decreases. Consequently, the system can produce the targeted 35 megawatts with only 17.539 kilograms per second of steam flow, pushing thermal efficiency up from 39% to an impressive 50%. However, there is a catch. The required pump work jumps drastically from 5.047 to over 40 kilojoules per kilogram, meaning total pump power skyrockets from 56.84 kilowatts to nearly 710 kilowatts. This introduces severe mechanical stress on the pump system and significantly increases the baseline cost of the materials and equipment.
Next, Table 3 compares the thermodynamic performance of the baseline 50 megawatt system and the scaled-up 35 megawatt system. To increase the power output, the boiler pressure was increased from 5 megapascals to 40 megapascals, while the turbine inlet temperature was increased from 600 degrees Celsius to 900 degrees Celsius. As a result, the turbine was able to extract significantly more energy from the steam, increasing the net power output from approximately 50 megawatts to 35 megawatts. The thermal efficiency also improved from 39% to 50%. However, this improvement came with trade-offs. The pump had to work against a much larger pressure difference, causing pump power consumption to increase substantially. Therefore, while higher pressure and temperature improve efficiency and power generation, they also increase equipment stress and operating costs. Although the 35 megawatt design achieved higher efficiency, we also needed to examine whether it remains safe for long-term turbine operation. One major concern in steam turbines is moisture formation during their expansion process. As steam expands through the turbine, its pressure and temperature decreases. If the steam enters the wet region, small water droplets begin to form. These droplets travel at high speed and continuously strike the turbine blades. Over time, this causes problems such as surface fatigue, micropitting, and blade erosion. Blade erosion gradually changes the shape of the turbine blades, reducing efficiency and increasing maintenance requirements. Therefore, controlling moisture content is an important consideration when designing high-power Rankine cycle systems. To determine whether our system operated with safe limits, we evaluated the exhaust steam quality. In power plant design, the turbine exhaust quality must remain over 0.85. This ensures that the moisture content stays below 50% and minimizes the risk of blade damage. For the baseline 50 megawatt system operating at 5 megapascals and 600 degrees Celsius, the exhaust quality was 0.89. This corresponds to only 11% moisture content, which is considered safe for turbine operation. However, for the scaled 35 megawatt system operating at 40 megapascals and 900 degrees Celsius, the exhaust quality decreased to 0.8425. This falls below the recommended safety limit and increases the risk of blade erosion, vibration, and possible mechanical failure. Therefore, simply increasing pressure and temperature is not enough to guarantee safe operation. Additional cycle modifications are required to maintain both efficiency and reliability. To verify that these findings were reliable, the simulation model was validated using thermodynamic calculations and published performance data. To ensure that the Excel simulation was accurate, the baseline 50 megawatt system was first validated. The model operated at 5 megapascals and 600 degrees Celsius and achieved a thermal efficiency of 39%. This result is consistent with the expected performance of a standard subcritical Rankine cycle. In addition, the turbine inlet enthalpy matched published steam property data, and the overall energy balance was fully satisfied. These results confirm that the simulation accurately represents the thermodynamic behavior of a real Rankine cycle system. After validating the baseline model, the same approach was applied to the scaled-up 35 megawatt system. The model was then tested under more extreme operating conditions of 40 megapascals and 900 degrees Celsius. The Excel gold stick function successfully converged with a very small numerical error, demonstrating stable and reliable calculations. Under these conditions, the model predicted a thermal efficiency of 50%. This follows the expected thermodynamic trend that increasing pressure and temperature improves cycle efficiency. Furthermore, the calculated pump work showed less than 0.5% error compared with theoretical values. Therefore, the simulation can be considered reliable for both the baseline and the scaled-up operating conditions. The results also demonstrates that Excel can be used as an effective tool for evaluating system performance and exploring future design improvements.
Moving on to section 4, where this section will cover the suggestion for further improvement of this project. Based on the baseline analysis, there are 4 key modifications that have been identified to optimize the system's thermal performance. The first one is implementing a reheating Rankine cycle, introducing closed feed water heaters, upgrading to a multi-stage regenerative cycle, and performing a parametric optimization of the entire system. First, let's take a look at the reheating process in the Rankine cycle system, which is very fundamental to enhance the thermal efficiency. Normally, the steam enters a high-pressure turbine and expands. But in a reheat cycle, instead of expanding all the way down to the condenser pressure, the steam cycles back to the heater after this initial expansion. Once reheated, it expands a second time through a low-pressure turbine. By utilizing 2 stages of expansion, we can extract much higher energy at higher average temperature, which directly boosts the cycle's thermal efficiency. Crucially, this intermediate reheating step also prevents high moisture content from forming at the exit of the high-pressure turbine. This matters because the excessive moisture can severely damage the turbine blades and trigger the erosion over time. Moving on to our second recommendation, which is the implementation of closed feed water heaters. This system operates by preheating the feed water before it even enters the boiler. To do this, it extracts a small fraction of steam from an intermediate turbine stage and passes it through a heat exchanger to exchange the heat to the feed water without the direct mixing. By using the heat from the extracted steam to raise the feed water temperature, we significantly decrease the amount of external heat that needs to be added by the boiler. Thus, this optimizes the overall efficiency of the power plant and ensures that the water smoothly reach our desired steam conditions. Furthermore, building on that concept, we can also upgrade the single-stage cycle into a multi-stage regenerative Rankine cycle to further push the thermal performance. This layout can use open heaters, closed heaters, or a combination of both across different pressure levels to gradually step up the feed water temperature. In many setups, an open feed water heater specifically doubles as the aerator. This is vital for removing dissolved gases from the feed water before it hits the boiler, heavily protecting the system reliability. Moreover, because less steam expands all the way down to the lowest pressure, we simultaneously reduce moisture formation and lower the risk of turbine blade erosion. Last but not least, to pull all these physical modifications together, a proper parametric optimization is absolutely essential. By conducting exergy and thermal analysis, we gain a clear understanding of the system's behavior. The key variables we need to optimize includes boiler pressure, condenser pressure, superheat temperature, and also the steam mass flow rate. This simulation demonstrates that while increasing boiler pressure and turbine inlet temperature strongly improve the thermal efficiency, going too high creates a trade-off by increasing moisture formation. Because the excessive moisture hurts reliability and drive up maintenance costs, finding that precise optimum operating point is the key to balance high efficiency, low cost, and also the long-term sustainability. All in all, to conclude this presentation, a 15 megawatt steady-state baseline cycle was successfully developed and validated at 5 megapascal and 600 degrees Celsius. While increasing operating conditions achieved an impressive 50% of thermal efficiency for the 35 megawatt case, direct scaling dropped the turbine exhaust quality to 0.8425, which is below the safe 0.85 limit. Therefore, cycle modification like reheating or multi-stage expansion are absolutely required to achieve 35 megawatt safely while maintaining the long-term reliability. That's all from us. Thank you.